Good afternoon. This is the Whipple Award Lecture. My name is Bruce Tchaikovsky. I'm the president of the Planetary Sciences section, and one of the fun things to be able to do is to introduce the award recipient, and it's my distinct honor to be able to introduce Roger Phillips today. The Whipple Award is named after Fred Whipple, who, of course, was the inventor of comets back in the 1940s. The Whipple Lecture is the highest honor that the Planetary Sciences section gives out. And if you think about the contributions that Fred Whipple made, it related to putting planetary science on a firm quantitative basis and taking novel approaches, measurements, and techniques to move the science forward. And I think that our recipient, Roger Phillips, embodies that. And I'd like to read a couple of words from the nomination letter that was submitted for him to get this award, because I think it sums up very well the role he's played and the contributions he's made. Few people have had a greater influence on the field of planetary science. His career encompasses the full breadth of work required to advance planetary science. He has developed new means of probing the planets, new methods of interpreting the data, mentored many planetary scientists, and served on numerous NASA missions and advisory panels. He's extremely highly regarded throughout the field as a rigorous, creative, insightful scientist and a stimulating colleague. I couldn't agree with that more, and I think that summarizes the role that Roger has played. Before I let Roger talk, I have a couple of parting gifts that he gets. The first, Roger, if you could come up here. The first is the certificate from the Planetary Sciences section, artfully produced by the AGU. It says, Planetary Sciences section recognizes Roger Phillips, the 2008 Whipple Lecturer for Terrestrial Planet Geophysics. So, Roger, let me present this to you.
Thank you very much. There's more.
And in their infinite wisdom, the AGU has decided that you get a certificate not only for giving the lecture, but for receiving the award. And it's my pleasure now to give Roger the 2008 Whipple Award, presented to Roger J. Phillips, and I found out, by the way, that the J stands for J, for outstanding contributions to the field of planetary sciences, presented by the Planetary Sciences section.
Thank you very much. Thanks, Bruce.
And without further ado, I will turn it over to Roger.
Thank you very much, Bruce, for the kind words. I appreciate this award very much from both the Planetary Sciences section and from the AGU, and for all my colleagues who helped make this happen. It's a live mic, right? Okay, I don't need to use that. I could have given you a half an hour of really boring stuff, and I decided instead to attempt to avoid that and take kind of a retrospective look back at both the field of terrestrial planetary geophysics, which is not that old, or depending on how you measure, and also take a look back at some of the things that I've done with my colleagues over the last 30 or 40 years. So hopefully this will be in places amusing. This is probably one of my last chances to basically embarrass my colleagues in public. I'm sure I will have many more opportunities to embarrass myself in public. So that's not a problem, I don't think. Everybody applauds. So, planetary physics is a discipline that's underpinned by theory, but certainly fueled by spacecraft observations. It's helped us understand the basic structure of a planet, its thermal evolution, its relationship to the surface features. What I'm going to do is talk about a few of the pioneers in terrestrial planet geophysics over the last 40 years, and longer actually. And my choices are very selective, and then I'll lapse into something called Along the Way, and with some of my friends who may not be my friends after this, but we'll see. So who was the first terrestrial planetary geophysics? It's arguable, but I pick Laplace, who in 1799 first noted the differences in lunar moments of inertia were not in equilibrium with the current orbital state. He was the first to note it. By the end of the 19th century, people had noticed, we were talking about the fossil bulge on the moon. Runcorn spent half of his career saying that convection was the cause of all this. Some of us said a little bit later, no, not really. Finally, fossil bulge in a viscoelastic moon, perhaps a former high eccentricity orbit in a 3/2 resonance state from Garrick Bethel, grad student at MIT. So you can see the progression of great lunar thinkers from Laplace to Jeffreys to Garrick Bethel, perhaps, or we'll see. Talk about a few people. You can't talk about terrestrial planetary geophysics when you talk about Bill Kalla, who was a giant and had major contributions to the field. One of the things he did in the 60s, in order to master a topic, he would simply write a book about it. And in quick succession, he wrote the theory of satellite geodesy, which essentially became the starting point for understanding how to use spacecraft in orbit around planets to basically understand planetary gravity fields. We went on to write, a couple of years later, Introduction to Planetary Physics. One of the interesting things that Bill did was he once produced a paper in order to get a poem published. It's true. The 7 Ages of a Planet. Our system is a stage, and both the sun and planets are merely players. They had their birth and have their fiery end. The planet in its time plays many parts. Its acts mean 7 ages, and it ends up last seen. That ends its history. Its quiescence time, sans melt, sans plate, sans almost everything. His idea of how terrestrial planets evolved going through the well-defined stages was essentially a jumping off place that we use to understand how the terrestrial planets evolve, and we spend a lot of time trying to, when a planet doesn't behave like Bill said it should, trying to figure out why that is. Talk about another topic. Well, a couple months ago, I gave a talk at the DPS on lunar geophysics and constraints on the lunar interior. And Jerry Schubert, asked me a question after the talk, said, why didn't you talk about lunar electrical conductivity? And I said, truthfully, I forgot. So I'm using this opportunity to kind of make up for that lapse at the DPS. They carried out, Chuck Sonnet and Jerry Schubert carried out an experiment having to do with Apollo that gave us a deep insight into the thermal structure of the moon. And it started out with the recognition that electromagnetic induction could be measured in the moon. It could be inverted to produce a lunar conductivity profile. In turn, that could be inverted to produce a temperature profile of the moon. They employed a technique where Explorer 35, far from the moon, measured the primary inducing field, and then lunar surface magnetometer on the surface basically measured the sum of the primary plus induced field, and you can essentially get a transfer function that way, and then you can invert the transfer function for lunar electrical conductivity. Later approaches concentrated on looking at the induced dipole moment transient events, but the early work was this 2-magnetometer experiment. Also, a significant research program was carried out to characterize the conductivity temperature relationship of lunar materials. If you think about that, those days, Al Duba comes to mind. I show his picture, but the only one I could find on the web, he had a carrot on his nose, so I didn't want to show that. The bottom of the slide shows the theory for all this that Jerry Schubert published in the first issue of the Moon in 1969. This fuzzy picture on the left is Chuck Sonnet and Palmer Dial discussing the Apollo 12 magnetometer experiment in Ames. And 19th of November, 1969, Alan Beam deploys the magnetometer. You can see the 3 booms of the magnetometer right there during the first EVA on Apollo 12. The transfer function, both normal and tangential transfer function carried all the information. It was this information that was inverted to basically determine a conductivity profile, and the conductivity profile was used to invert to get a temperature profile. And they published some landmark papers in Nature and in the proceedings of the Second Lunar Science Conference, basically coming up with the first lunar temperature structure. A lot of people worked on that problem over the next 10 years or so. Lon Hood gave a nice review of this. in the Origin of the Moon book in 1986, which summarized all the different estimates of lunar conductivity profile, and using some of his own work, he reviewed some of his own work where he used conductivity temperature relationships for different materials to invert to get temperature profiles, and all of them show that deep in the moon, basically the solidest temperatures should be achieved with a conductivity profile. Now there's another, well, changing topics now to gravity. There's a guy named Jack Lorell, who probably most of you have never heard of unless some old-time JPL people are. I see a few of those in the audience. He worked on gravity. He was on the celestial mechanics team for Mariner 9, and they produced, right around 1971-72, they produced the first spherical harmonic gravity, planetary gravity field outside of the Earth, as far as I know. It certainly was the first one for Mars. You can see this very low degree field. Tharsis kind of stands out, and Utopia kind of stands out, and other things that probably stand out aren't real, but nevertheless they're on the right track. Here's a paper they published in Science back at that time. Here is another figure from that paper showing the actual surface topography as determined at that time from Earth-based radar, and the equivalent surface height from the gravity field. And you can see there are hints of gravity models that to be, and we go all the way forward to MRL. Obviously, we have exquisite gravity models of Mars right now. But here's how it started back 35 years ago or so. With advice from Jack, I was able to put together a Bogey gravity profile of the Moon using Earth-based radar data and using the Mariner 9 spherical harmonic coefficients, paying lots of attention to air analysis. So I think this is the first real Bogey gravity anomaly of Mars, and it gave us some hints that Tharsis is in fact not quite isostatic, which we know to be the case today. Don Turcotte made a whole lot of contributions, as you know, to planetary science, planetary geophysics. I mentioned here just two of them. He got heavily into the business of parameterized convection, which sprung upon the scene in the late 1970s. Here's a figure from Scenes, the Lunar Science Conference, and you can see a couple of temperature profiles, different initial conditions, different boundary conditions. Parameterized convections allowed people like me with slow, dumb computers to do thermal history models of planetary bodies, and I did that for the next 10 or 15 years. Another thing he did was look at thermoelastic stresses from a cooling body. He wrote a paper that was elegantly simple in trying to explain the physics of a cooling elastic shell, and it essentially involved two parameters. It involved the blocking temperature at the base, which defined the base of the elastic lithosphere, and it defined the change in internal temperature, and there's some very simple curves. And people since that time have done much more sophisticated models, but the basic physics essentially tied up in these two equations and this one graph. And of course, all of you know the book that he did with Jerry Schubert, which we can call Planetary Geophysics 101, that a lot of us use in our classes over the years and occasionally and turn to for nuggets of wisdom. And I probably wore out about 2 or 3 copies of this book along about a 20-year stretch. Sean Solomon obviously made fundamental and broad contributions to terrestrial planet geophysics. I just point out one of his contributions in collaboration with Jim Head, where when everybody was talking about a plume up as a cause of the Tharsis rise, he and Jim came out with the idea that it's really primarily a constructional feature, a volcanic constructional feature. And they were basically right, at least the first order, and I think that paper is still going back a long time, still holds a lot of nuggets of wisdom about what's really going on in Tharsis. This is a more recent picture of Sean. This is how Sean was at a party about a year before the Messenger launched, and things weren't going particularly swimmingly. So I think that's what he was thinking. I'm not sure. I mentioned Jay Melosh partly as a cheap plug to basically say, yeah, Messenger turned out okay. Here's an image from the first flyby, and Sean didn't need to worry so much after all. But Jay has done a lot of work, obviously, in impact cratering, but he's also done a lot of work in tectonics. And this is one of his kind of classic papers where he looked at the stress distribution and the subsequent tectonic response of a despun planet, and he used this to apply to Mars, and in combination with a cooling planet. He looked he reviewed the fact the distribution of, in fact, the azimuth of thrust faults or wrinkle ridges on let's say Mars, I meant Mercury, on Mercury, and they seem to be not isotropic, as you might expect from a simple cooling planet, although they suspect there was a lighting bias in these plots of azimuth. Messenger will solve the problem of the distribution and azimuth of thrust faults and wrinkle ridges on Mars, and by the time Messenger is done, we'll have a good handle on, I think, on the cooling history and the de-spinning history and a lot of other things. Should be one of the major geophysical contributions from that mission. Also back in the day, people were determining seismic velocity profiles of the moon. This is the original and classic velocity profile produced by Nafitaxos that was mostly derived from basically artificial impact on the moon, like stages of the Apollo rocket system, occasionally a lunar module when it was no longer needed, and derived this sort of 60, 65 kilometer thick lunar crust, which was around for decades, including a break in it, which at the time I thought was a closing of fractures. Since that time, people have looked at other sets of data looking at different ways. The mean lunar crustal thickness seems to be decreasing. The profile that you get within the crust seems to be changing depending on what data set you use. So this time, our understanding of lunar crustal structure from seismic data is kind of unraveled in a sense. But on the other hand, I think it's firmer that we think the crust is thinner than it used to be back in Apollo days. Well, let me just go on to some of my own wanderings with some of my friends, just to show you what I used to do. This is my Buddy Holly phase, and I started out in mining geology as a undergraduate and a graduate student, and my first real job in geology was in a place called Red Mountain. It's near Berthoud Pass in Colorado, and ironically about 30 miles as the crow flies from where I live now. A career in mining geology quickly morphed logically into a career in plasma physics, which is what I was doing as a graduate student at Berkeley across the bay here. And I was doing this work to support the idea that we could send a sounding radar at low frequency and understand the interior of the moon from orbit from the Apollo service module. And so I spent my years in Berkeley trying to do plasma physics and figure that out. We eventually did that. We flew a radar around the moon on Apollo 17. Here is the Apollo Lunar Sounder Experiment Team in 1971 on the porch of the old LPI, the old West Mansion, about a couple years after it opened. You won't recognize too many people here. This is Tommy Thompson right here, still kicking. Good. Here's the Ron Evans Command Module pilot. Here's me with long sideburns. This is my thesis advisor, and so therefore the academic grandfather of a bunch of people in this room who never even heard of this guy. Dan Ward is probably one of the co-founders of what was called at the time mining geophysics, and he'd come down from Toronto to start a group at Berkeley in the engineering school in the Department of Mineral Technology in the Hearst building in Berkeley, and involved, besides Stan, there was a geochemist named Herb Hawks involved and a geologist involved, and I somehow migrated, I won't go through the details, I migrated to work with Stan, who about halfway through my career, they got interested in this radar sounder, so that's how I kind of got into planetary science. Here's when we actually did the experiment. This is the VHF antenna on the surface module of Apollo. Is Ron Evans actually retrieving the film that the radar data was recorded on during the trans-Earth coast after the mission. Here's some data, stereo pair of data on the far side of the moon from the lowest frequency of the sounder that we used to construct the first stereo model of the moon. Just to go forward for a moment before I can go back to where I was before, 35 years later, I'm still doing radar, involved with the Sherrod radar, and with some really neat data through polar caps and low bait debriefments and other places on Mars. You heard Jeff will probably talk about some of this stuff shortly, Jeff Plout. And we also figured out that from the radar that the substrate wasn't deflecting very much. I'd like to point out a couple of people who have been really important in this Sherrod business, MRI. One is Rich Zurich, who in fact, is a tireless MRO project scientist who basically stands there and takes all the incoming bullets for the science team and basically deflects them somehow and kind of leaves us alone to kind of run the mission instruments and do the science. The other guy worth mentioning is now a good friend of mine, a guy named Fabrizio Bernardini, who lives in Rome. He's the unsung hero of Charade. He's the brains behind the hardware digital subsystem on Charade, and he continues to work with me decoding the raw radar data so we can process it in Boulder and produce radargrams. And that's a new estimate of elastic thickness from the radar, which is completely different from any other estimate of elastic thickness, and I think it's probably more or less correct. It's the most assumption-free estimate you can make of elastic thickness. Well, meanwhile, back in the early days of JPL, while I was working at Apollo, I hooked up with a guy named Jim Whitcomb. If you're in the NSF Geophysics program, you know this guy. I knew him as an undergraduate at Colorado Mines, and we hooked up again in Pasadena. And this was the heyday of the dilatation hypothesis for earthquake prediction, where it's shown that you could have predicted the 1971 San Fernando earthquake if only you had known how the dilatation theory works. So we used magnetotellurics to go out in various places, both Antelope Valley and Bob Hope's Ranch in Thousand Oaks, to basically see if we could see changes in apparent resistivity and correlate those changes with earthquakes. And we kind of sort of did, but never quite proved it, and Jim was kind of aghast at the whole thing, being a proper seismologist, well, how you could use electromagnetic waves to do anything. Meanwhile, I was learning about potential theory at the same time, and non-uniqueness of potential fields. I was trying to get involved with that. I already mentioned my working with Jack Laurel. And it turned out JPL at the time, had a great graphics department. You can make neat pictures for lots of money. So how to be non-unique is real-logical, minimize shear strain energy, maximum stress levels, test a model, or use divine inspiration to beat the non-uniqueness and trying to interpret potential fields. I try to use divine inspiration most of the time, and it was reasonably successful. Bill Shogan's a guy who is retired now and became famous in 1968 with the discovery of mascons on the cover of Science at some issue in 1968. Basically, the fear was that they didn't know the gravity field well enough to land the Apollo spacecraft from the moon, and the mascon anomaly were going to throw the spacecraft completely off. It became a big deal. Eventually, of course, they did land successfully on the moon. Bill worked with me on the first Venus gravity data from Pioneer Venus in the late 70s, and here's some of the line of sight gravity anomalies from Pioneer Venus that we first got, and we also attempted to make a planetary spectra of the gravity power in Venus, spherical harmonic spectrum comparing against the Earth and Mars and Venus and Mars and the Moon, and decided that Venus was more Earth-like, which turned out to be kind of true, I think, as compared to Mars and the Moon. Work with Norm Sleep. We had a series of meetings called the Tharsis Workshops. The first one was in Vail, Colorado in 1977. We've had them in various places. The most recent one, typically they're in Colorado, but the most recent one was at Keystone, I believe, in the year 2000. So it's probably time to have another Tharsis Workshop. But Norm and I got to know each other at that time, and he and I worked on a model for isostatic model for Tharsis that may or may not be correct at this point, and it showed that the crust was thin under Tharsis, but the mantle density was less than the surrounding mantle density. And that part may still be true in terms of a residuum underneath the Tharsis uplift, a topic I published on later. I worked with Bill and other people and Norm on the follow-up to Bill's brilliant paper. Bill Kalla wrote a paper that essentially figured out that you could use the Tharsis and assume a symmetry about Tharsis in second-degree terms and separate the non-hydrostatic from the hydrostatic contribution to the J2 spherical harmonic gravity coefficient and come up with a really good estimate of the moment of inertia before we had precession data to get the real moment of inertia. And his estimate was right on what turned out to be the real moment of inertia measured later using Pathfinder data compared to Viking. This is a follow-up paper that Norm and Bill and I worked on, and added some things to it. For example, that if you used a moment of inertia too low, as others were proposing, Bruce Bills, I guess, was proposing that the stress type was incorrect in terms of predicting ballast mariners. Here's a letter from Bill to me in 1989, in a very precise Bill way. Here's my draft. It's on a printed out and on a 5.25-inch diskette IBM comp DOS MS Word contra and so forth. Very precise Bill Collins telling you exactly what he did down to the last detail, so you can figure out, so you can actually read it. This is back in the early days of personal computers, of course. I worked with Mike Magellan for quite a while back in the 70s and early 80s. I went back to my CV and found out we published 5 papers together. A lot of people think Mike's an irascible guy, but he's really a sweetheart if you get to know him. Anyway, this is a paper probably the first paper we did together. It was on Ganymede, and it was on my newfound knowledge of how to do parameterized convection, thanks to people like Don Turcotte. And we hooked up a parameterized convection model for Ganymede with a viscous relaxation model for craters, and came up with predictions of crater statistics versus basically numbers versus density distributions as a function of the heat source content inside of Ganymede, and we use this model to predict what that crater distribution should look like depending on what the heat sources were. And I'm not sure we ever tested it. We sure liked the idea of hooking up the parameterized convection model with the viscous relaxation of craters. We published a chapter in the first Venus book. On the left is an attempt to look at stability and whether the Venus lithosphere should subduct, still using parameterized convection modeling and still influenced by Don. Here below is a figure of gravity, the real gravity, line of sight gravity over beta, a couple of different models where we figured out the depth and compensation at beta Regio on Venus should be 300 or 400 kilometers. I think that's still probably true. Somehow, I forget how, Sean Solomon reviewed this. I don't know whether the editor, Don Hunton, gave it to him or we asked him to do it, but I was at LPI at the time, and Sean reviewed it. Here's his letter from July of 1982, and he says, "In all, you and Mike have done a nice job." He has some comments. All these are minor. Yeah, right. There's like 5 pages of dense things you should do to fix this paper. He goes on to say, "I'm confused by page 22." He finishes off that paragraph with, "A little elaboration will save this page from permanent opacity." And I was wondering what all this meant. I wasn't quite sure how to read all this. And 7 or 8 years later, Bob Grimm showed up to be my postdoc at SMU, and he brought with him a graduate student's guide to Sean speak. I'm not making this up. So okay, nice job is kind of like okay, it means good enough. And confusing means idiotic. More to the point, I'm confused by this section of your paper means this is pretty poorly written. I think you need to do some fairly heavy rewriting, or more likely, your logic is totally flawed. I think you should probably throw away everything you've done for the last 3 months. So apparently Sean handed off his red pen to Bill Kalla, and we were at that time, this is late 80s and early 90s, we were working on trying to convince the powers that be that after the nominal Magellan mission was over, we should use aerobraking and circularize the orbits so we could get a really good gravity field. So here's a draft of the white paper for Geophysics and Magellan mission, and Bill Kalla says, "This is very good as far as it goes." I looked it up in Sean speak, and it's so embarrassing, I don't even want to tell you what the interpretation of that is. But here's a piece in Science where we, in fact, made a presentation to the Space Science Advisory Board. Eventually, NASA bought off on it, and we did that. And Magellan turned out to be the first spacecraft air-braking successfully, placing Magellan in approximately circular orbit. And people, since that time, have used that circular orbit data to boldly expand the degree and order of the Venus gravity field up to degree 180. Here's our moderator. This is Bruce. I had the pleasure of working with Bruce in the last 10 years. Started with my sabbatical at LASP in the year 2000. This is the way Bruce dresses for his Maven science meetings. He thinks that PI means king, and most of his co-Is think it's kind of weird, but they haven't got the courage to point this out to him. But at the same time, I congratulate Bruce for of course, getting the Mars Scout mission Maven. So seriously, this is a good thing. It's okay if he keeps wearing this costume. It's fine. We published a paper in Nature on Mars volatile and climate history. It was a pleasure working with Bruce. This is a diagram trying to relate everything to everything in that paper. For a talk I gave this morning, in fact, I thought I could improve on that, and that's what this is. And it turns out the real version of this has arrows flying in and flying out and interconnecting. And by the time I finished it, I was so confused I didn't use it this morning in my talk. But I spent so much time on it, I just thought I'd show it here. I worked with Ray Arvidsson. One of the things, and that was a pleasure. One of the things we worked on was the fabled resurfacing history of Venus that many of you know about. And and it turns out that here's a comment by Alan Stofan that essentially you can't use craters to figure anything out on Venus. Here are some of the models that we talked about at the time. The end-member models, the catastrophic resurfacing model, the equilibrium resurfacing model, and a hybrid model that we at Washington University liked the best. One of the problems with all this work was that people took the end members more seriously than any of us ever intended. Started attacking the end members, where we all kind of thought, well, something in the middle really is probably what happened. Steve Hauk, who I think is giving me a talk later on this session, published a paper, and he followed on his undergraduate thesis work, I think, when he came to St. Louis, showing that, in fact, that there are an infinite number of ways in terms of resurfacing models that can fit the observed crater population, and a model that actually has a wide spread in surface edges actually fits the data better than a random model. Nobody reads this paper. And in fact, I heard 2 papers this morning where people, in fact, say the random crater distribution on Venus must mean there's an episodic resurfacing. Worked with Matt Golombek over the years. We haven't done a whole lot together. This is Matt. He looks just about the same today. Not much different. I can't tell any difference, can you? One of the things that we've done lately, I looked at, we haven't published too many papers together, but in fact, we just finished a paper called Mars Tectonics in a book on Cambridge University Press. We spent a long time on this paper. We submitted it December 7th of 2004. It said, the day will live in infamy. We got it back, accepted in October 2005. Then nothing happened for 3 years because other chapters of the book were languishing and we didn't feel like revising it. And so finally it looks like the book was going to come together and revise it this last summer. And once you know that people have been publishing papers on tectonics over the 4-year period, and so we had to kind of rewrite the paper. And so I got to write this paper twice, and I guess it's coming out in the spring. This chapter in this book, the whole book is coming out. We published, with my friends, we published a paper, on loading of Tharsis and the Tharsis bulge and the Arabia bulge and the trough around Tharsis. This may not stand the test of time. I don't know whether how much of that. Nothing you publish ever stands the test of time. But what happened when we published the paper was that we did a quick calculation back to AMBUB. We figured out from the model that there was about 300 million cubic kilometers of magmatic products at Tharsis, and we took estimates of how much CO2 and water might be in the Tharsis magmas and came up with there's enough CO2 to produce a 1.5 bar atmosphere and 120 meter thick global layer of water, and this may have made Mars clement for a time due to Tharsis outgassing. And that's all the press seized on in the paper. All this great geophysics we thought nobody cared about. They cared about this silly little calculation. Here's the headline from the first page of the St. Louis Post-Dispatch. Washington University team may have found key to life on Mars. Here's Science Times. Mars calamity may have created conditions for life. So I learned about getting along with Science magazine in that particular episode. Other thing I did at last was work with Mike Mellon. It was a great pleasure to do that. We published a paper on gullies and sort of a confined aquifer that basically bursts through obliquity cycles and temperature diffusion. Here's a drawing on the whiteboard in my office at LASP, and here is the figure it turned into in the paper. We still believe this model may work in some cases, but maybe not work at all. Clearly it can't work everywhere. We're worried about the permeability, but it was a fun model to put together. It was a pleasure working with Mike. Over the last 20 years, going back to sometime I think in the late 80s, I'm working with a bunch of folks who I've come to really enjoy being with, call it the Magellan Gang, which we started out as a radar, turned into a laser altimeter. Mars Observer blew up. We hung on. We did Mars Global Surveyor, went to orbit in 1997. We're still kind of together. A lot of us are on Messenger, and still more of us or some subset of us are on the Grail mission. So we're still kind of hanging together. Zuber and Smith and Solomon and all these, and Jim Head and all these folks. And we used to have some really interesting meetings where we really just simply talked science for 3 days, and it was great. Here's Dave Smith, illuminated, trying to convince us that time variations of Mars and J1 are not noise. I guess he convinced us in the end. The slide transition, in 2003, Jim Head doggedly hangs on to a 35mm slide collection, which numbers in the millions. I think I remember a place called Treasure Island back at Brown, where there were a gazillion slides, and there was a security guard in front of the door, I believe. And there was a door behind the door where the really good stuff was, which I was never really able to get to. Then Maria Zuber had moved on years ago. She saw the change coming. She did it instantly, of course, and Jim was still looking at slides. We had a number of interesting meetings in Montana. He was coming out from dinner one night. Jeff Andrews Hanna trying to look cool. Maria can't be bothered. Greg Newman stopped and tried to take a picture, desperately trying to pose while swimming simultaneously nonchalant. I found one decent picture of mentoring. This is at an LPSC Chile kickoff, probably around 1990, plus or minus a year. And we're posing and pretending we're eating very hot chili peppers. Bob and Robbie actually are eating them. Sue and I know better. You can draw your own conclusions. So here's another view here's a view of the Magellan Gang, and it involves a number of people I've talked about in this discussion. You can see Jerry Schubert and Bill Colla and Jim Head and Sean Solomon and Ray Arvidsson and so forth. That was probably background. Also probably around 1990. And some other people in this room. So that's it. Every 10 or 15 years I have to change jobs. People get wise. And so I moved on from Washington University to Boulder, Colorado. They're advertising essentially for my replacement right now at Washington University. If you're so interested, you might want to apply. If we get a young Roger Phillips now, that's a really bad idea, so we need to get somebody else. So thanks a lot.
Thank you, Roger. We have time for some questions. Can we bring the lights up?
Yes, Bill.
That was a lovely talk. Can you speak more about the lunar crustal thickness? That seems really very confusing.
Say that again, please.
Can you speak more about the lunar crustal thickness? What do you really think?
I think that it's the thickness underneath the Apollo sites is probably more like 35 kilometers or 40 kilometers, and not the 65 kilometers that were determined from Apollo. I think the newer analyses are stronger analyses. I don't think we understand the profile, seismic velocity profile in the crust very well, but I think we understand the thickness better. This, of course, changes all the mass balance for the composition of the moon by a lot. Yeah.
Anybody want their turn at retribution for the pictures? I'll get mine later.
Uh-oh.
Well, in that case, Roger, thank you very much again, and it's our honor to be able to honor you today.
Thank you very much. Thank you.